All right, today what we're going to do is measure the instantaneous rate of change at a given point precisely. What we did last time was we took a point 0, 0, and then what we saw was that if you took a bunch of points and we took the tangent lines from, or the secant lines from 0, 0 to those points, those things all had slopes, which are the average rates of change over those regions. And as these points came closer and closer to 0, 0, that rate of change seemed like it was approaching the value 20. It went from 19.9 to 19.99, 19.99999. But we want to know for sure, first of all, that it would actually get to 20, or not get to 20, but that those things actually converge to 20. And it's not conversion to some tiny number that's just a little bit less than 20, but not 20 itself. And in order to figure out exactly what values those things converge to, we want to know precisely what the limit is that we're trying to find. So let's say, let's get rid of these red x's here. And let's say we have a value x and it has, of course, height f of x. And if I go forward by some, I'm going to pick up a value, some x plus h here. So I'm moving forward by h. And it's going to have height f of x plus h. And so the average rate of change of this function over this region is the slope of this line here, right? It is going to be this difference minus or divided by that difference. Well, what those things are f of x plus h minus f of x over h, and right, that's my rise. It's this difference between this term and that term, and my run is x plus h minus x, which is just h. And what we want is to take this point and move it closer and closer towards f of x itself, which means we want this h to get smaller and smaller and smaller. So what we're looking at is the limit as h approaches 0 of f of x plus h minus f of x over h. And this thing here is defined to be f prime of x, or the derivative of f with respect to x, and it's the instantaneous rate of change of f at x. And so what does that have to do with our specific function here? So let's work that out. In our specific function, the limit as h approaches 0 of f of x plus h minus f of x over h, that thing is, well, f of x plus h is minus 5 times x plus h squared plus 20 x plus h, from which we're going to subtract f of x, minus 5x squared plus 20x. And this is all over h, and we're taking the limit as h approaches 0. So what that will give us here we just distribute the negative, so we have plus 5x squared minus 20x. And over here we have minus 5x squared minus 10xh minus 5h squared plus 20x plus 20h. Sorry if that's a little bit tough to read, but it's just the algebraic expansion of these terms. So if you're following along, you would get the right thing here. And so what we see, here, let me write this out a little bit bigger. Minus 5x squared minus 10xh minus 5h squared plus 20x plus 20h plus 5x squared minus 20x over h. All right, then let's start looking to see what's going to go away. So we have minus 5x squared plus 5x squared, those cancel. Minus 20x plus 20x, those cancel. So what we have left is the limit as h approaches 0 of minus 10xh minus 5h squared plus 20h over h. But we should note that there is every summand in my numerator has an h expression in it, so I could factor all of it out. So I pull an h out, I get minus 10x minus 5h plus 20. That's all over h. Those can cancel. And I'm looking at the limit as h approaches 0 of minus 10x minus 5h plus 20. And now, if I plug 0 in here, I get minus 10x plus 20. And that thing is my f prime of x for this particular curve. And so let's examine that for a second. First of all, I couldn't just plug 0 in here, right? If I plug 0 in here, I get f of x minus f of x, which is 0 on the top, divided by 0 on the bottom, which doesn't make any sense. That's a total non sequitur. But by taking this limit and evaluating this thing algebraically, I am able to get to an expression where I could plug in my 0, and what I'm left with is a h-free term, a simple algebraic expression. Now, how does this translate into the behavior for a curve? What it says is that when x is 0, my initial speed upwards is 20 meters per second, which is what we suspected from the previous video, right? It's the thing we started with finding. I just plugged 0 in for x. What it also means is that if I plug in 1, it's only 10, and that makes sense, right? Once I shoot my rocket up, it's going slower and slower. At 2 seconds, this expression is 0, and that makes sense because I've stopped, right? It shoots up in the air, the gravity slows it down, it stops at the top, and then it starts falling back towards the Earth. So in 3 seconds, I get minus 30 plus 20, which is minus 10, and that makes sense because now instead of my height increasing, it's decreasing. So my rate of change is negative. And then in 4 seconds, it hits the ground at minus 20 meters per second, the same speed you launched it at. And so this is a bit of a simplification of what would happen in real life. Like, we don't have any air resistance or anything like that. But barring some minor factors like that, this is the essential principle of how things like this behave. And so the point of all of this is that this thing here defines the derivative. That is the limit that we're trying to find. And your goal in being able to take this and extract something meaningful from it, algebraically what that means is simplification of this expression algebraically, canceling out the h here and getting rid of it so that you can plug 0 in and get a meaningful expression.